All right, guys. So it's 2 p.m. So I guess let's get this workshop started then. So welcome to SRIL Robotics Innovation Lab's Workshop 3 of the 2021 SRIL Gravity Card Challenge. We would like to begin by acknowledging that this presentation is being broadcasted from Surrey, British Columbia, Canada, located on the traditional and unceded territories of the Coast Salish peoples. So I'm Daniel. You might remember me from the past two workshops. On behalf of the entire Surrey Robotics Innovation Lab team, I just want to welcome everyone. Thank you for spending your Saturday afternoon with us, and we are excited today to empower the use of science. So just a little bit about Surrey Robotics Innovation Lab. We are a nonprofit organization dedicated to empowering youth innovators through STEM. And we host events like these every summer for hundreds of youth. And our partners include City of Surrey, Surrey Schools, UBC Center for Community Engaged Learning, and SFU. And we are incredibly grateful to UBC Center for Community Engaged Learning for awarding us with the Connect to Community grant. This support makes it possible for us to host events like these. All right, so at this time, let's take our screenshot then. So if you could kindly turn your camera on, put on a nice smile for us. We'll take the screenshot for our sponsors. So we'd like to see your beautiful smiles.
Give us a smile. Oh, seems like we're kind of shy today on the camera. Oh, well. Thanks, Jeremy. I appreciate your camera. Smile.
Yeah. All right, we got it?
We have got it.
All right, Clay.
Excellent.
All right, then. Now I would like to encourage you all to give us a hand for today's presenter, Clement. And also let's give a hand for you all for participating in this workshop and making this event possible. All right, Clay, take it away.
Okie dokie. Well, let's begin with the entire idea of the science behind gravity cars. We probably are all familiar with science, but we're going to focus on one part of it today, physics. But now, what is physics? Oops, I wasn't supposed to go to that slide. You didn't see anything. I'm going to ask you, what do you think physics is? Why don't you give me a reply in the chat? It's okay to guess. We'll figure it out soon. I see practical math. Good response, Joey. Logic, I like that. We'll give you about 2 minutes. You have plenty of time. Science about how things work together in everyday life. Gravity, math applied to the real world. The laws of the universe, I like that one. Science experiments. Thanks, Daniel. The best kind of science. Yeah, I love physics, but is it the best? I don't know. Big smart things that I'm not going to pretend to know. Oh, you don't have to pretend to know. You will know them, or a little bit of it by the end of this workshop. The reason why I can't go the speed of light. Very much true. Yes, matter and energy. I like that. Energy and nature. Ooh, bring out the big guns. Quantum physics, quantum mechanics, and Schrodinger's. Ooh, that's a little bit far-fetched, but yeah, you're all on the right track. Okay, so just a quick introduction. You guys already nailed it. So physics is a fundamental building block of science, along with chemistry and biology. Now, as you have explained in the chat, it does explain the events in nature. This is through our observations and through the logic we interpret from the things we observe. However, our explanations focuses on the idea of matter interacting with energy and back and forth. And this answers the questions of why and how things happen. Now, as you may have pointed out with all those fancy items that you gave me, quantum mechanics, physics equations, Schrodinger's, there's math. There's lots of math. But we'll get on to that in a little bit. Okay, so let's begin with matter. So now I will ask you another question. Now that we've got that brain ideas flowing, what's matter? And please don't tell me matter matters, because that's an old joke. It matters, but matter matters. Yes. Yay. Okie dokie. Oh no. Take a look at the background. What do you see in the background? That would be a better question. I see. Matter is stuff. Yes, you have three phases of, some of the phases of matter. So you have solid, liquid, gas. You also have plasma, but we won't be going into that. I see someone brought up plasma. Cool. I see there's a lot of stuff that says volume and mass. That is the exact definition of matter. Excellent. So matter is anything that takes up volume and mass. Now, of course, let's quickly tell us what these things are. They're fancy words. Now, volume is just taking up space. If you can imagine anything on Earth, we're taking up space. We're a ball floating in space. So we're floating there in this three-dimensional sphere thing. So volume just means we take up space. Now, mass is something different. This is interesting because mass is actually defined as the resistance of an object to acceleration. It's kind of strange. Fascinating. Thanks, Daniel. You know, how do I mute Daniel Louis from SRIL? The Earth is round. Thanks. I wish I could kick him, but I'd get in trouble. Well, back to mass, though. So this is the idea of resistance to acceleration. Now, note, this is not the same thing as weight. Now, there is a law in regards to mass where we cannot create mass and we cannot destroy mass. So whatever mass we have in the galaxy is the amount of mass that there is. There's no more mass. There's no less mass. Dark matter, I don't know what that is. No one knows what that is, but we'll figure it out someday. But for now, this makes sense. Mass in is equal to mass out. Mass is not created or destroyed. So now that we have the idea of the basics of physics down, we can get to more fancy parts of physics, scalars and vectors. So both vectors and scalars are a way to measure things. Now, what are we measuring? Well, a scalar is a quantity with a magnitude, but a vector has a quantity, so a magnitude, a number, and a direction. It has to be going somewhere. So now, armed with a little bit of knowledge, let's try this activity. Is the following a vector of a scalar? I'll read them out one by one, and we'll be writing yes or no. All right. Is acceleration a vector? Or, oh, Why is it a yes or no question? Write vector or scalar. Don't use yes or no. Is acceleration a vector or a scalar? Go ahead. Write down vector, write down scalar. Which one is it? Don't worry, we all make mistakes. Even if you're right, even if you're wrong, there's always a chance. Now, I see a lot of vectors, and it is indeed a vector. So typically when you work with acceleration, you have a direction. So let's say I drop a piece of plastic and it goes faster. It's going faster in a very specific direction. It only accelerates, it only gets faster downwards. And that's the entire idea of a vector. It's going faster at some rate, and it has a direction. So now what about speed? What about this one? A lot of scalars? Yes, it is a scalar. So the great thing about a scalar is it's just a number. So I can throw the same piece of plastic and you can tell me how fast it's going. It doesn't matter which way it's going. It can be going up, down, left, or right. And it'll eventually, well, you can give me a number. But now what if I wanted that same number in a specific direction? What about velocity? Yes, I can already see we're on the right track. It's a vector. So a vector is basically similar to a scalar, but all it contains is a direction, and that's really all it is. So speed is a scalar version, velocity is the vector version. Distance is a scalar, displacement is distance in a direction, so it's a vector. Now here's a difficult one. I'm going to give you the idea, what is the difference between velocity and acceleration? So velocity is the speed of an object in a direction. So if you can see this piece of plastic gliding across the screen on my little icon in the corner, or wherever it is on your screen, you can tell me this is going a specific speed in a direction. In my case, I think on your screens it's probably going to the right, or is it going to the left? I'm not entirely sure, but you can tell me this is going some speed in some direction. Now, acceleration is the change of the speed. We'll get into this a little bit more, but acceleration is the change of velocity. So if we start really slow and go really fast, the difference between the starting velocity and the end velocity is known as acceleration. But it'll make more sense in a little bit as we go on. Now, here's a tricky question. This is the last part of this activity. Can you tell me if weight is a scalar or a vector? I see. You see, this was actually a trick question. So, weight is actually the force of gravity. And gravity is only one direction. It's always down. In our case, gravity is that way, to the Earth. And because it has a direction, weight is a force. Because weight is a force, and a force has direction, it is actually a vector quantity. We'll get into a little bit more of how this gravitational force actually is weight, but I thought that would be a nice trick question to put in at the start. Okay, Now we're familiar with vectors and scalars. Kind of, maybe, hopefully. But we will move into forces. So first of all, we gotta start with the big man himself, Sir Isaac Newton. So he was an English physicist and mathematician. He came up with the idea of gravity, supposedly because of an apple that fell on his head. Now, he is also well known for his 3 laws of motion. All right. Does anyone here know the first law? No. All right. Yeah, there's the first law. So, an object in motion stays in motion, and an object at rest stays at rest. I am sitting on a spinny chair, so it can spin, it can rotate. Now, as long as I do not do anything, I'm not spinning. My feet are off the ground, and I'm just sitting in my chair, and I am not spinning. And likewise, if I'm spinning, I will keep spinning. Now, if there was no gravity and we ignored friction, I would be spinning forever. I would never stop. This is the idea of inertia. Oh, I see a third law. Yeah, we'll get there. So, as I mentioned, the only reason I stop is because there's friction from my chair, which is acting against my motion, which will eventually make it stop again. Now, there's actually a correlation here. I don't know if anyone knows a second law, but we'll just bring it up here. So the force acting on an object is proportional to the multiplication of its mass and acceleration. So the force that is applied to an object is equal to whatever that object's mass is times its acceleration. I see, and some of us are already ahead for the third law of motion, that every action has an equal and opposite reaction. Now, all these concepts will be a little bit important moving forwards. So, let's get into forces. We have 2 types of forces, contact forces and action at a distance forces. Contact forces are things that have to touch together, as the name suggests. And action at a distance forces are ones where you don't have them to physically touch. Now, some examples of contact forces and action at a distance forces are as follows. We can start with contact forces. Friction. We'll do a little bit of a demonstration on that in a little bit. We also have elastic or spring forces, which will have a spring or tension. Applied force, if I push my monitor, I'm applying a force because I'm physically tilting it down. And normal force, Normal force comes from the third law. Every action has an equal and opposite reaction. If I am pushing on the wall in my bedroom, it does not move, even though I'm putting force on it. It is actually pushing back at me with a normal force. And this is the idea of an I can't speak. Think. This is the idea that every action has an equal and opposite reaction. So the harder I push against that wall, it's always going to be equal to me. So it's always going to push me back. And we're not going anywhere. So that is our contact forces, or some contact forces. If we look at action at a distance forces, we have gravity, magnetism, and electric force. Unfortunately, I do not have any magnets to demonstrate this with, but as you may know, you can actually use magnetic fields through objects. So if I had a piece of paper, I can put a magnet on the bottom and a magnet on the top, and I'm able to use the force of the bottom magnet to move the top magnet. And this is known as action at a distance. The items do not touch. Okay. Of course, now that we have the basics down, it's the part you've been excited about, math. Because who doesn't like math? So let's begin with talking about a few variables. Now, these are things that you have to put into equations. Oh, math is hard, Alex. I know it sure is. I know Daniel knows it's hard. He's sad about it. Hang on, Alan. It's not that bad. So, in the metric system, we have a few things that we measure things by. Force, of course, is measured in a unit named after Newton himself, the Newton, because force. Now, acceleration is measured in meter per second squared. I'll come back to this in a little bit. Mass is measured in kilograms. Time is measured in seconds. Velocity is measured in meters per second. And height, or in our case, usually you see distance, is measured in meters. So back to that question about the difference between velocity and acceleration. Well, if I want to find out how fast an item is going in a direction for velocity, I'm going to measure it by how many meters it goes in that direction divided by the amount of time it takes. So we get meters divided by seconds, meters per second. Now, if we want to find acceleration, we're going to see how fast the velocity changes or what that change in velocity is. So how do we measure this? We take velocity per second. So that is the units for acceleration. So meter per second divided by seconds, which gives you meters per second squared. And these are the variables that we will be working with. As scary as they are, it's probably going to get a little bit scarier. But don't worry, we'll make it kind of easy. Hopefully, maybe. Okay, formulas! Yay! Yeah, that's a big wall of text. We're not going to be using all the formulas. However, we will be focusing on this formula sheet here, except the electricity part, or the geometry part, or the trigonometry part, or the entire mechanics part. We'll be doing a little bit of it, but I just thought that I'd show you this. I noticed someone asked me, why are there integrals? Well, that's stuff you learn in university. If you ever take stuff in university, that's what you're going to learn in first year. So have fun with that. But if you're going to grade 12 and you're planning to take physics 12, this is the formula sheet you will see. So by the end of grade 12, if you take physics, you'll know what everything on this formula sheet is. It's still a lot of math. But we got to get started somewhere. So let's just take it easy and focus on just a couple of the equations. So, of course, you all are all wondering, how can I make my car go faster? Now, there are two forces at play here. In simple terms, you have gravity and you have friction. I think we should start with gravity. So here on Earth, the acceleration of an object due to gravity is a constant 9.8 meters per second squared. And now the force of gravity, as we mentioned earlier, is measured in newtons. This is also known as weight. So, in that idea, if you really wanted to lose weight, just go to another planet that has less gravity. So, you'll be lighter. It's all based on the acceleration. This actually all comes from Newton's second law. The force is based off mass of the object and its acceleration. Now, because here on Earth, the acceleration due to gravity is 9.8 meters per second, we know that, I don't remember, do I have an example? Yes. Okay. So before we'll come back to the slide. It's kind of in the wrong order, but we'll be right back to it. So now that we know what the acceleration due to gravity is, how about we do a quick example? If I have a mass of 1 kilogram on my desk here on Earth, what is the force of gravity acting on it? What is its weight? Write it down in the chat if you know the answer. Remember, mass is 1, and the acceleration due to gravity is 9.8. You have a 1 kilogram mass and a gravitational acceleration of 9.8. What is the force acting on the mass? I had a question here. I honestly do not know where it went. Unfortunately, it has disappeared. Ooh. Steven, you're really close. Ooh, 9.8. I want units. What are the units? That's the right number. Ooh, is it kilogram? Remember, a force is measured in what? There we go, newtons. Yay! You've done physics! So let's quickly go over the answer to this. So what is the gravitational force acting on a 1 kilogram mass on Earth? So 1 kilogram, plugging it into Newton's second law, 1 kilogram times the acceleration of 9.8 meters per second gives us 9.8 kilogram meter per second squared. But I don't like that unit of kilogram meter per second squared, so I'm just going to call it a Newton. And there we go. We have 1 times 9.8, which equals 9.8 newtons. Woo! We did physics. Now, let's take a look over here. Here's a little fun experiment that you can try. If you still don't believe me that objects on Earth accelerate at 9.8 meters per second square, you can grab 2 random objects, preferably not super heavy, hold them about the same height, and drop them. I can assure you that unless one object is a piece of paper, they will hit the ground at the same time. So there was once I believe Galileo was a scientist. He dropped balls off the Leaning Tower of Pisa. And what did they do? They were different sizes, but they hit the ground at the same time. Why is that? Ooh. Well, this is how we proved that the acceleration due to gravity is constant. It doesn't change. You can drop anything you want, and depending on the air friction involved, for the most part, it'll accelerate and hit the ground at the same time. 'Cause gravity. Woo! So, let's take a look at the other half of things. Friction. Now, friction is a force that resists motion. Let's try an activity again. I'm going to get everyone to take their hands and put them together. You're going, ooh, hold on, someone sent a comment. But this doesn't work on the moon. Some scientists proved it. It should work even better on the moon, Stephen, because the only thing that makes the gravitational pull different is, or the reason that things don't fall at the same rate is because of the air friction involved. In fact, if you have a vacuum, just like on the moon, it has a higher chance that both objects will hit the ground at the exact same time. I believe that the astronauts on the Apollo missions actually did the drop test with a hammer or something like that, and they did hit the ground at the same time. The moon does have gravity. It is significantly less than Earth. But off of that tangent, we're going to get back with a little activity. So take your hands, press them together, and rub them. You're going to try this, and then try to press your hands harder. And what happens if you go even faster? Type what you feel in the chat. I see. Yeah, your hands would be hot. They would create a lot of heat. No, please do not go as far as to deep fry your hands. That would be bad. No, okay, that's enough. Don't hurt yourselves. I see pain, so we're gonna stop. That's right. The more you press, it might have gotten harder, and the faster you go, the hotter you get. So friction is actually the force based off of its normal force, so how hard two objects are pressing together and opposing each other, and the coefficient of friction. Now there's a big word here, coefficient of friction. All that a coefficient really is, it just means that it's just a number that stays the same and we're multiplying something with it. We'll get into a little bit of an example of how this works in a little bit. So let's figure it out then. The formula of friction is mu, the coefficient of friction known as mu, times the normal force. Now, normal force, as we mentioned earlier, is from Newton's third law. An object, every action, the third law, every action has an equal and opposite reaction. The normal force is that opposite reaction. If I have my hand and I'm pressing with my other hand, the force against the hand that's pushing against the other hand is known as the normal force. And that's why when we pushed our hands harder, you may have realized it got harder and harder to move and more heat was generated. That's because you're increasing the normal force and creating more force of friction. So that gives us a little bit of an insight into how friction works. So now that we have some basic formulas, how do we get our gravity cars to go faster? Well, recall second law. In simple terms, F net is the sum of all the forces. So the force of gravity and the force of friction. Now we have the force of gravity that's giving us that force that moves our car, and we have the force of friction that's opposing it. Now, because they're vectors and they have directions, the force of friction is opposite to the force of gravity. They're opposing each other. That's why force of friction is negative. So force of gravity minus force of friction is equal to mass times acceleration. Hopefully this makes sense, but you'll see a little bit more of it as we move on. So we can also rewrite this as force of gravity minus the force of friction over mass is equal to the acceleration. This means your car will start to go faster, which means your car will go faster. And this can all be done by decreasing friction. Now you might be wondering, how do I decrease friction? Let's take a look at the math. So, all right, was that a question? Yes. So the way you want to get your car to go faster is to decrease friction. Now, you're probably wondering, just like you suggested, what if I want to make my car heavier? I'm going to add more mass to get a larger force of gravity. Well, the force of gravity, as we saw earlier, is the mass times 9.8. Now, if we substitute this into the equation, this is where it gets weird, we will notice that all the masses cancel each other out. It's like taking the same number and dividing it by the same number. We always get 1. 3 divided by 3 is 1. So because it's 1 multiplied by any number is still the number. 9.8 times 1 is still 9.8. So we can actually cross out the masses. And this happens in both equations for the force of gravity, because it's gravity, and the normal force, because the normal force is based off the pull of gravity, because if something's pulling down, the Earth that's creating the gravity is pushing back at us. So the force of gravity is equal to the normal force pressing back up on us. Is anyone lost? Just wondering. I know it's getting a little bit technical, so I'll just pause right here. Yes, a little bit. Is there anything you would like me to go back on in particular? It's fine. Okie dokie. I know it's a little bit confusing. It's not going to be really easy to see, but someday you're going to be sitting in your high school classroom and the teacher is going to say this and you're going to say, I remember this. The SRIL guy talked about it. But some of us have asked if I could explain it again. Sure, we'll go through it a little bit again. We'll just go through this slide, or let's head back one slide. So we have our formula, the force of gravity and the force of friction. We know that the combination of these two items will be equal to mass times acceleration. Now, we can actually rearrange this formula to see how the acceleration of the car is based off of the forces. So the force of gravity minus the force of friction divided by the car's mass gives you the acceleration of the car. Now, you want that number on the left side of that equation, Fg minus Ff over m, to be as big as possible. The bigger the acceleration number, the faster your car goes down that ramp. We'll get back to that. I saw a question, does less mass mean faster? Not necessarily. We'll get back to that. But in terms of forces, it doesn't matter what the mass is, because with a larger mass, we get a larger force of gravity. But the force of gravity is also used to make the force the normal force. And the normal force is used to get the force of friction. So if you make the force of gravity bigger by adding more mass, you make the normal force bigger. And then you have the normal force that's bigger that makes the force of friction bigger. So everything cancels itself out. That's why if we take a look at that last formula down there, all the masses, all the m's cancel each other out, which ends up giving you basically the same thing as you started with. The mass doesn't actually influence how fast the car goes. If you're talking about force, we will be getting to another part of this workshop where we'll show you where mass does matter. Now, first of all, if you're really interested in figuring out what the acceleration of your car is, we've got to do a little bit more complicated stuff. Now, our ramp is slanted at a 26-degree angle. This changes the direction of those vectors. Remember we talked how forces are vectors? Well, the force of gravity, the force of friction, they're all vectors, and they all change with the angle that the object is on. So, as we can see, the force of gravity is multiplied by sine of the angle of a ramp. In our case, the angle is 26 degrees. I won't go into much detail since this is no longer physics, it's just trigonometry. It's math for those of you who are interested. I think this is material you will learn in pre-calculus 10 or grade 10 math. You'll start to see this stuff. Now, this is used to change angles and blah, 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 and convert vectors for now. But all you're concerned about is you have the formulas. That's all we need to know here for now. Now, that's exactly what I just said. So, exactly what I mentioned, so we have to use sine and cosine. These are those SIN and COS buttons on your calculator. If you have a scientific calculator, that's what these are for. And this can be used in our formula, which gives us the force of gravity times the sine of the angle of the ramp minus the force of gravity cosine of the angle. Oh, we're missing a mu here. So there should be a mu. Sorry, this should be a force of friction. There's an error in the slide. I'll make sure I fix it for the slides when we send them out to you all. But this is how the formula writes out in the end. So that kind of concludes forces. I know it's a little bit math heavy and it's confusing because now we're messing with vectors. But maybe we can go look at something a little bit easier. Energy. This is a scalar. We don't have to worry about all those weird directions and vectors and blah, 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 arrows. Instead, we just have to worry about number is number. It is number. Easy. Kind of. So, without further ado, let's move into energy. So, they're like all the other stuff. I see. Yes, thanks, Alex. A number is a number. It's a number. It's easy, kind of. Dash SRIL guy. Okay, so let's begin with a little bit of the energy, the idea behind energy. So there's a law here. Just like we had with mass, energy cannot be created nor destroyed. It can only be transformed. So, why does this say forces? Weird. Ignore that. There's another typo. That's to say there are two types of energy. Potential energy and kinetic energy. How about we just create an energy list on our chat? If you can think of some form of energy that you can think of, write it down and maybe it'll pop up on the slide magically. Does no one know any ideas of energy? Ooh, I like that. Gas. Thermal energy. Yeah, now we're getting stuff. Gravitational energy. Sound energy. Mechanical, electrical, potential, kinetic. Yeah, energy. Nuclear energy. I like that. Let's pop them up. Yay. So, potential energies include magnetic, electric, elastic, and chemical. Kinetic energy is movement. That's it. Kinetic energy comes from movement and nothing else. If it's moving, it has kinetic energy. And then you have a ton of potential energies. Solar energy is an interesting one that someone has brought up. Solar energy would be probably in part of nuclear energy because it's from the sun, or it could be, well, actually, that's a really good example. The idea of solar energy. Remember, energy cannot be created or destroyed, but it can be transformed. So when we're talking about solar energy, we take that nuclear energy from the sun that comes down to Earth and we convert it. We change it into electric potential energy using solar panels. And this is some things that you will notice. Energies are being transformed and you don't even know it. Remember when we were rubbing our hands and you could feel the heat? You're actually converting that kinetic energy of your hands moving into the thermal energy. I would say it's a type of potential energy, but I forgot to put it in the list. But you're actually converting energies back and forth from one another. And voila, energy. So, quick reminder before we jump into more math. Here are your variables. The force in Newton. We won't be using that anymore. Acceleration in meter per second squared. We won't be using that anymore. Mass in kilograms. We will be using mass. Time in seconds. we'll be using time. Velocity, we'll be using that too. And height, or distance, in meters. That is also going to be used in our calculations for energy. So, here are the simple energy formulas. The potential energy from gravity when your car is at the top of that hill is equal to the mass of your car times the gravity, the gravitational pull, which is 9.8, and height, which is how high the ramp is. It is 1 meter high, if you are wondering. Now, the kinetic energy is equal to 1/2 times mass times the velocity squared. If you're wondering what is a square, it's a fancy way about saying that item is multiplied by the same thing. So let's say we have 3 times 3. 3 times 3 equals 9. We can also say that as 3 squared is equal to 9. Hopefully that makes sense in case some of you do not know what that little 2 that's floating in the air means. It is the meaning of squared. That V is multiplied by V again. So, like I mentioned earlier, these are scalar quantities. They're much easier to work with. They don't have a direction. But they're still numbers, and numbers are numbers, and they're kind of easy-ish, as usual. So, now we will talk about the correlation and the relationship of these energies in your car. So, we realize that the mass times gravity times height, your potential energy, will be converted into your kinetic energy, which is calculated with 1/2 mv squared. And using these equations, we can change the energies from one point to another. Now, if we take a look at that little fancy ball graphic that I bet all of you are looking at right now, you will probably see a ball going whoop, 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 up and down, up and down, up and down. And we can see there are letters and graphs saying EG and EK. Energy to gravity, EG, or your gravitational potential energy, is the maximum when it's at the very, very top of that curve. So it's when it's very high up, you have the most potential energy. And you also notice that the ball stops. So your kinetic energy is 0. But as it goes down that hill and goes faster and faster, we start losing that gravitational potential energy. Where is it going? It's going into that kinetic energy. It's being converted. And this is the same thing that's happening in your gravity car. You start with that gravitational potential energy, it rolls all the way down, and then it loops all the way back up. Well, it doesn't loop in the gravity car, but you get the point. It goes down and it goes faster. And that is the principle of energy with the gravity car. Ooh. Of course, you might be wondering, so how can I make my car faster now that I know about energy? Well, if you put mass higher up the ramp, you actually have more time for it to accelerate. Your energy will also be greater because your mass is higher up. I'm going to leave it to you to interpret how this is actually calculated. But I think you are now armed with all the formulas, all the variables, and all the math needed to find out how fast your gravity car is going to go. And I know it's not on the slides, but if you're wondering how fast your car will go at the bottom of the slope, all you have to do is solve for that V. Change the equation, shuffle it around, and you will end up with the answer for V. In fact, do you guys want me to write it down? I can write it down right now. Yes, yes, okay, let's write it down then. Okay, dokie. Let me get my settings. Okay. So a little bit of a math crash course right now. So we have, oh, what's happening with my lines? Hello? Okay. So we have our formula. mgh is equal to 1/2 mv squared. So now we have to solve for this value right here, which is, oops, v. So the way we do this is we can actually move things around. We take this 2 from the bottom, we get 2 mgh. We move that m from one side to the other, so we divide both sides by m. The m's cancel out, and we get this equation. 2gh is equal to v squared. Now, how do we solve for velocity? Well, all we have to do now is use another thing on your calculator known as square root. This is the opposite of square. So it looks like this. This is the formula for square root. It looks like a check mark with a big line on top of it. And that will cancel out the squared sign. And this is how you find velocity. So now, as a recap, in all of the equations that we found out, mass doesn't do anything. It always cancels out. But the thing that matters is where you put that mass. And just remember, though, as you design your gravity car, one of the biggest challenges is figuring out how to use your mass effectively. That is probably the most challenging thing on the gravity car. So, hopefully this helps you figure out how your car will perform. And maybe we'll start to see some really cool designs. Well, I think it's time to conclude with a concluding activity. Now that you are all experts on forces and energy, let's talk about, oh, hang on, someone brought up another part, air resistance. Now, I could talk about air resistance. However, it's very, very, very confusing. It's actually so confusing that you won't learn about it until second year or third year university. It's not something I hope to actually talk about here, because the difference of the air friction on your car is so minimal that it won't give you a huge beneficial gain of speed. While yes, if you have a rounded design, it might go a little bit faster. It's not actually worth putting the math into it here. The car is so small and your numbers are going to be so tiny, we can almost round it down to 0. So for this purposes, we are actually ignoring air resistance and air friction. But what you should be worrying about is that friction from rolling down the hill based off your force of gravity and where you put the masses so you can get the most energy out of your car. All right, without further ado, now that you're all experts on energy and forces, let's have a small activity to conclude the last workshop of the Gravity Car Challenge. Ooh, I'm on annotate mode. Okay, this is your activity. Using the things that we learned today, can you answer these questions in the chat? So, here in British Columbia, Canada, our electricity provider is known as BC Hydro. Hydro being another word for water. So, in the chat, explain, using the physics that we learned today, how do we use water to make electricity? Go! Ooh, I can see some really, really good responses. Well, some good responses. But You have a lot more words in your vocabulary right now. Build me a big paragraph with words and stuff. I appreciate the creativity here. That's nice. Okay, let's start reading through some of the answers. Water push wheel, wheel make power. Yes. In simple terms, yes. I see Rena has announced kinetic energy. What kinetic energy? It doesn't come from nowhere. It has to come from somewhere. Where did we get that from? I don't know what kinetic energy is. I'm gonna pass that one. Thanks for writing in the chat though. Matthew has posted. There's a big tank full of electric eels that touch conductive metals. I don't think that's gonna work. And as far as I'm concerned, aren't eels saltwater aquatic animals? Most of our power is generated with fresh water. So good luck finding electric eels in fresh water. But unfortunately, I'm pretty sure that's not how we create energy or electricity here in BC. Oh, water stream goes through a turbine, which rotates it and connects to a generator, then makes energy. Yes. But now we want to know, where does that energy come from? It comes from the force of gravity. Yes, the force of gravity is pulling down. Let's see if anyone has anything else on here. Water pushes the turbine. Ooh, yes. Water go burr. Well, I'm pretty sure you all know what this is. Yeah, this chat confuses me too. It's all good. It's a good thing you guys are all enjoying it and having fun with your responses. But I'll quickly wrap it up then. For those of you that did respond, thank you. You are all on the right track. That energy is pulled by gravity. This gives it that potential energy. And that force pulling down takes it into that turbine. And we start using that normal force, the equal and opposite reaction, to start spinning our turbine. Using that turbine, we change that potential energy into our kinetic energy. Now this kinetic energy is just kinetic. We need electricity. So we put it through a generator and it turns into our electricity. And there you go. Forces to energy to electricity, which is energy. You guys have a lot more to go. Don't give up. You're all good. Don't worry. Like, sometimes you learn things here, sometimes you learn things there. It's all about learning. We all make mistakes. And it's great that you guys are stepping out of your comfort zone to write things in this chat, since it's wonderful to learn from each other and communicate our ideas and thoughts with one another. So excellent work, everyone. I like that quote, Andrew. There are no accidents, from Master Oogway. If anyone doesn't know what that is, it's from Kung Fu Panda. So it's a movie that came out a long while ago, made 2008, so 13 years ago. Yeah. Well, without further ado, that is the last slide of the last workshop. And I really hope that you guys enjoyed our 3 workshops. And that is the end. So if you have any questions to ask to us about the physics or anything, it is time for us to give you the floor. You can type in the chat, or if you want to unmute your mic and give us some words or some feedback or some questions, go ahead. And if anyone asks or if anyone goes to click that link, just please be aware that that is probably a Rickroll. I'm pretty certain that's a Rickroll, so do not click that. Why? Because someone just hang on. I got a real quick story though. Someone sent me that link to Rickroll me one day. It was actually yesterday. And the thing that happened is I didn't get Rickrolled because an ad played.
Oh yeah, sometimes an ad plays.
So I was able to read the title description before I got rickrolled. So no, do not click that link unless you're going to get rickrolled. All righty. I'll hand it on to Daniel for some closing remarks.
Yep. So I just wanted to say that even though this is the last workshop of our Gravity Card Challenge series, we do have one more workshop coming up in a few weeks in the middle to late August, where we have a guest speaker who is currently a university student on an internship with Tesla, speaking about his work experience as a Tesla intern. So we will be sending out an email about that, and we would love to have you come to that workshop as well. And as well, I would also like to open the floor to any questions, not just from this workshop, but from the past workshops as well. So if you have any questions about CAD, right, about maybe how to use Autodesk Inventor, it is a pretty complex piece of software. If you want to ask me some questions right now, or any other questions, you can also ask as well.
Actually, Daniel, on the topic of that, I did get a few questions in regards to how do you get, yeah, Matthew right there has asked it again. How do I get the student version of Autodesk Inventor? Would you like to take this?
If you just go on Google and you search Autodesk Inventor student license, it will bring you to a website. Okay, so I'm not sure if something has changed. Prior to 2021, they allowed basically any student to get an inventor license. I don't know if they changed it. So maybe they only allow university students. I'm not sure. But basically, you go in through a process, right? You have to submit just like a transcript or something of your enrollment at a school, and they will give you a license, right? So you can try that. If that doesn't work, then I'm sorry, but you can still download just the full version, just a regular personal license of Inventor, and you will get a free trial, unless that has changed as well. So if you can't, yeah, so if you can't get the student version, don't worry, just download the regular version, and you will get a free trial for like a month. A month should be longer, like maybe I don't know if it's a month, but it should be enough for you to do the what you need to do for this summer event, right? All right. How wide are the wheels? The wheels are 9 millimeters thick. 9 millimeters thick, and their diameter is 30 millimeters. Was it?
Yep, that is right. And just in case anyone missed it, there have been some adjustments to the size of the cars. The cars are now allowed to be 140 millimeters long, so you get 40 millimeters more length. The width is still 50 millimeters, and the height is still 40 millimeters. So, but you can make your car longer now. So that was a vote that we had in the previous workshop too, and that is the only difference to the Gravity Car Challenge itself.
Yep. And someone asked, how do you submit your car design? We're gonna send out an email with a Google form, and we're going to ask you to please submit your STL file. So that is your file that you export for 3D printing, and also your, if you're using Inventor, we'll also ask for your IPT file, which is your Inventor CAD file, the file that is native to Autodesk Inventor. And that's because if there are any problems, if we see any problems with your part, we can go into the Inventor file and make some small edits for you to make it if there are problems. Any other questions?
I see a lot of memes in the chat.
Mm-hmm.
Well, we technically did give them the floor of the chat, right? We just basically gave them chat, so.
Yeah. What was the size? Oh, I'm just gonna type the size into the chat for everyone then. The size limit, it's 140 millimeters by 50 millimeters
Yep, by 40.
by 40 millimeters. And what is that? That is length times
Length with height.
width times height.
Yeah. Hmm. All right, if there are no more questions, the time is now 3:05, so we will be wrapping up this workshop. Again, we thank you all for coming to this workshop. We really appreciate it, and we wish you all the best. Just letting you know that there is that Tesla speaker coming in the next few weeks. You'll get an email about that. And we wish you the best with your gravity cars.